leave at least a few minutes for some Q&A at the end.
Thank you.
So what is AI really? As probably everyone knows, it's really just a bunch of linear algebra organized in very complicated ways. So it turns out there's a bunch of different ways you can do linear algebra with computers. One is the CPU, which is extremely programmable, minimally parallelizable, but widely available. There's GPU, which is very programmable and extremely parallelizable, but at least for WebGPU is still being deployed. And then NPU, which is dedicated hardware for AI, which is very power and performance optimized. These different things on the web with the CPU, you can obviously use either JavaScript or WebAssembly, with WebAssembly generally being more performant. For GPU, there was WebGPL, long live WebGPU, and this is now shipping, which is super exciting, but still with limited reach. And to access the NPU space, we have WebNN, which you'll be hearing more about later. So if you put those together, here's a model I stole from other people, describing how some of this work. You can have a model that gets loaded into any of these different runtimes like TensorFlow, Onyx, and MediaPipe. Then you can go to the CPU through, like I said, JavaScript WebAssembly, through the GPU through WebGPU, or through WebNN, which, as you'll see, can actually target both CPU, GPU, and NPU. So how has the ecosystem looked over the last few years? Well, TensorFlow JS usage is growing massively, up 27x since 2020. Onyx has also become much more rapidly in just the last year or two, a very relevant player in this space, and is heavily employed, as you'll see, by Transformers JS and Hugging Face. And then MediaPipe is also seeing a huge number of downloads and utility within Google and outside. So obviously, when it comes to AI, you can ship your own model, and what people have called bring your BYO AI or have called DIY AI, what I'm calling compute abstractions based AI, which is to say on top of Wasm, WebGPU, and WebNN. But we also have these lovely higher level built-in APIs that Kenji talked earlier in the day about. Compute abstractions generally offer a lot more control and flexibility, which appeals to a certain segment of the population, especially those folks who want to do their own custom AI. Built-in AI is a much more turnkey solution, which naturally appeals to developers who are just trying to get things done, and I just want to use this bit of functionality. And so it's this basically just a long form of that, but with built-in models, you have no model download, which is really huge, no serving of the model, which can cost a lot of money for web developers, and it's very trustable and reliable. You can just go use it and expect it to work pretty reasonably. And models can also get better independent of developers updating them. So the advantages of the compute abstraction approach is that you don't take a dependency on Chrome, Google, or the web. You can get faster cross-browser support by targeting the primitives. There's more agency in which exact model you utilize. I know the built-in effort also has some efforts to try to let you have more influence on which model gets used. And it's also smaller in terms of CPU and RAM usage, obviously, than spinning up an entire LLM. This is a use case breakdown to just talk about this. Don't pay too much attention to the faces on the right. This is one person's perspective on how ready these use cases are for compute abstraction-based implementation, but to just run through this so we have something concrete to think about. Photo and video editing works reasonably well. Media stream manipulation, like background blur that we're very familiar with, works pretty well. Photo, audio, and video generation, kind of so-so. Same for speech to text. Image recognition, classification, and OCR can be done pretty effectively in these compute abstractions. Writing, summarization, and the kind of traditional LLM back and forth does not work that well. These models are extremely large and take up a lot of resources, which is a struggle for compute abstraction-based approaches. Text classification, like Fin and Simplicity, is much more tractable. Encoding, again, requires very long context windows and high quality, making it almost perfectly unideal for client-side compute abstractions. With that, we're just going to dive into each of the three different technologies. There is WebAssembly. WebAssembly is a portable abstraction over the CPU. Probably most of you know this. Execution is supported across browsers and devices. It can execute basically anything that you can actually compile to Wasm, which is basically anything. It's a better fit for smaller workloads where CPU bring up is expensive, or that workload that isn't massively parallelizable. And for a very large model, this can be a bottleneck. But today, most production applications that use AI on the web use CPU inference, partly because WebGPU hasn't been widely deployed, and partly because CPUs are a very reliable target. Every computer has a CPU that you can utilize. and that's not always the case for GPUs. In terms of future development with Wasm, we are hoping to extend features for CPU compute, including memory 64, FP16 floating point, and runtime improvements, as well as better interoperable with other web APIs like the JS promise integration and better memory controls. Just to briefly cover two of these, larger memories with Wasm 64. I think we all get this, right? You now can actually address a lot more memory space, and that can be relevant for some of these very large models. And then JS promise integration is an API to bridge the gap between synchronous application and asynchronous web APIs, which comes up all the time in the WebAssembly world, and this will be a huge benefit. A quick example, I really love this one, studio lighting, where you can put artificial lights into the actual scene and have AI generate all of this, and this happens with MediaPipe and WebAssembly SIMD. Same thing. There's also a lot of Hugging Face models, like sentence similarity, dictation, and others. So next up is WebGPU. Go through this pretty quickly. But GPUs excel when you need very high memory bandwidth and very high arithmetic intensity. And this stuff has been happening on GPUs for a while. You can see our roadmap here, but generally we are trying to expose low-level features that squeeze out even more performance around memory and arithmetic, like SIMD level arithmetic and smaller numeric types for linear algebra. This is all meant to just enable WebGPU to operate on these AI use cases more effectively. Some challenges that we're still working on addressing is definitely reach. WebGPU isn't everywhere, and ML-focused features aren't also everywhere additionally. And so that can be a hard support matrix to deal with. And of course, in terms of complexity, it is just a hard to optimize device-specific parameterization. And it can be important for the actual frameworks to utilize WebGPU effectively, which is complicated. WebLLM on WebGPU is one example that you can go and actually try out. And it's pretty cool to see an LLM running just entirely on these compute abstractions, though I will note that the quality is not exactly in line with what you can get from server-driven LLM models. And that brings us to WebNN, which we're going to cover.
Hi. So I'm gonna ignore the web and talk about the native ecosystem first. Companies are shipping devices with NPUs that Thomas mentioned. They are accelerated processors for ML workloads, and OSs are providing tools to access them. On Windows, it provides direct ML that lets you target NPUs from hardware vendors like Qualcomm and Intel. And on Mac OS, they provide a framework called Core ML to target Apple Neural Engine. That's how they call their NPUs. And on Android, you would use like LightRT to target our TPU. So if we want web developers to utilize NPUs, how do we do that? That's what we're working on with WebNN. So WebNN stands for Web Neural Network. It's an API to run neural network inference that leverages hardware acceleration. It's the only way for developers to reach NPUs from the web. And it's currently actively developed by Microsoft, Intel, and Google developers. So why is it called WebNN but not WebNPU? Since we already have Wasm for CPU and WebGPU for GPU. So the reality is right now, NPUs are only exposed through high-level APIs like CoreML, and NPUs don't have full operator coverage. There's no way for you to only target NPUs right now. Like OS frameworks like CoreML, it prioritizes being functionally complete, so it distributes the workloads across all available compute units. That's like NPU, CPU, and GPU. So therefore, we like the WebNN sits on top of these high-level APIs that we're basically a thin translation layer to target these high-level APIs. So this is what the flow looks like on the web. we have this JavaScript framework, Onyx Runtime or like RT or some other popular frameworks, and they can run the model by passing the model to WebNN, which is a thin translation layer to underlying ML framework model representations. So WebNN heavily rely on these ML frameworks to determine which hardware a model is compatible with and build the most efficient execution plan. Note that the JS framework can still target Wasm and WebGPU directly so that you can fill in gaps in WebNN to optimize pipelines and avoid readbacks when data is only on CPU or GPU for non-ML tasks. I'm going to give a little bit of detail on the WebNN implementation. So basically, it's like a graph building API that has a pretty high level representation of the model. Like for example, in this example, we're like just having a multiply and add node with input A and B and also a constant input. So like and then you build the graph using this JavaScript API, and then when you call builder.build, it compiles the graph to model a platform-specific backend representation. The backend representation is pretty much the same as how we represent it within WebNN. Like the level of abstraction is pretty much the same. Like the graph on the right that I show is similar to how we represent it in memory, as well as how like frameworks like CoreML represented underlyingly. So next slide. So after you build a graph, you execute it. You execute the model. The important part is the data could be large, so it's important to manage them efficiently and avoid readbacks to JavaScript. So we manage the input output and in the future weights in object called ML tensor, and it's remotely allocated by WebNN service backend so that it is easily accessed by the actual compute core when you actually get the inference run. If you have a pipeline of chain inference, since all the dispatch is async, you wouldn't need any readbacks to JavaScript for the inference running in between. So you just like WebNN internally will manage all the task dependencies, and you just need to read like whenever you want to synchronize it, you will read the final output by waiting on the final output getting written. So that's what WebNN does right now, and I'm going to talk a little bit about our ongoing work and challenges. One of the major ongoing work is WebGPU interop. Because we have a lot of use cases that really want to that have like non-ML workloads that is on WebGPU. So we really want to avoid data copies between WebNN and WebGPU. So so as you see on the right, these are like we are creating like a flag in the ML tensor to hint to the user agents that we want this buffer to be importable to WebGPU. And we will need to add we're working on adding a method to the WebGPU to import an external buffer from WebNN. And this will potentially allow zero copy between WebGPU and WebNN in some cases. So currently, WebNN has 92 operators implemented across all backends. With some caveats. So first is it's still not functionally complete in terms that you cannot run arbitrary workloads, ML workloads with WebNN. Like the 92 operators already covers a lot of the most popular models, but we still have edge cases to cover. So we're working on a core offset to address all the primitives to reach the breadth of ML workloads. Secondly, with the supported operators, there are differences about supported sets of data types and ranks for a lot of operators across backends. So we do allow feature detection through a method called op support limits. And we expect the JS frameworks to probe it to decide what models to deploy or how they partition the graphs. Another challenge is, as I said, we expose some level of feature detection on a high level, but there are a lot of fine-grained limitations across backends. So that, for example, some parameters are not supported on a particular backend, and WebNN try to decompose it so that it always succeed. But when we decompose it, there is potentially a performance cost, which could be very hard for developers to figure out why it's slower now if I change it a little bit. So right now we expose flags to allow dumping the final serialized model. So then developers can examine them and see, oh, it gets decomposed to an inefficient representation. The hope is WebNN, like once we get more usage, then it will encourage our underlying ML frameworks to expand their capabilities to minimize the need of decompositions that we need to handle. A couple other ongoing work is, one is we are working on like our LightRT JavaScript framework to like we're contributing to the WebNN delegate for LightRT, so that for apps that use LightRT, they can like once we finish this implementation, they can just like target WebNN directly without with meaningful effort. Another thing is model caching. We want to both. So right now, it's like slightly different from the cache we talked about in the previous talks. We want to cache the compiled model because both the download takes time, as well as like our underlying frameworks, they actually have a separate representation for the compiled model. And our solution is we want users to be able to save the model, and then later we return a key to them, and then later they can retrieve the model. That's like our underlying backend specific compiled model, and they will, yeah, and they can just run inference with the compiled model without rebuilding the model again. Back to you.
So there are some interesting challenges. I'm just going to leave this up and then open it up to questions and comments. But some of the things that we've been working on in this space and trying to figure out is, one, exposing what hardware is available. If you're leaving it up to the developer to pick some of these different paths, they might need to know how good is the GPU that I locally have? How good are these various different options? Can I even run the workload I want to run on this device, or should I just give up and go to the server? Anyone who's worked on the web knows exposing this kind of stuff can be tricky because fingerprinting and other reasons. And then, can WebNN effectively expose NPUs across these operating systems? Native has moved to ahead of time compilation for a lot of these things. Will the web always lag behind in having to do this kind of more JIT-based approach based on the specific architecture? And given radically different NPU designs, like optimized for int32 versus float16, can the same model be reused efficiently across devices? Very related to that first point. And of course, developers can choose to either use WebNN, which, as we covered, can go CPU, GPU, and NPU, or they can utilize WebGPU plus Wasm just for CPU and GPU access. But they can't really do both. Or I would be surprised if we ended up in a world where a single developer on a single website ended up employing both approaches. And so what signals should we be looking at in the ecosystem to understand which direction developers are going? That's it. Any questions? There's a lot of content. There's got to be some thoughts out there. All right, here we go. Ken.
All right. So I really wanted to ask that question. It's right there on the whiteboard. In your experience so far trying to deploy some models with NPUs, like, is there a portable like data type that you can use if the matrices or whatever the model weights are sufficiently small? Can you actually get the same model deployed across Windows, Mac, and Android NPUs with WebNN?
I think probably not. So because they have, yeah.
Surprise.
Yeah, I think the data type is optimized differently on different NPUs. Like Caramel, it only runs FP16, and we haven't really tested our TPUs, but I heard like it's better for ints.
Okay.
Yeah.
Can I answer that question?
Yeah.
I do know that CoreML and other frameworks are moving toward a model where you do have hybrid underneath the covers. It's not all run on the NPU. Some of it is and some of it isn't. And they go and rearrange the graph so that what can be run on the NPU is run on the NPU. So yeah, just do it behind your back. And then as for the last bullet point, I would like it to be the case that in the future, if WebNN is available in your browser, not available everywhere, you can just use it and it will decide whether to do CPU, which is the equivalent of Wasm, or WebGPU, equivalent of what on the GPU, or NPU at this case. That's the dream.
So my understanding is that mobile devices typically don't have strong NPUs, unfortunately. I think on Android, WebNN is kind of a little bit of a question mark for that reason. That's an interesting discussion, I think.
Yeah, we're right now the one of the challenges that we have with WebNN, as sort of discussed here, is that a lot of this stuff is still very new, like NPUs. We don't have a we don't have an OpenGL of NPUs. There's no real standardization about what these devices can do. And so what we have today with WebNN is sort of our best current approximation of an abstraction. But there are some examples where it's going to be challenging, like if NPUs on some devices really prefer floating point, some really prefer integer, then that's going to be a compatibility issue. The other thing is that just the actual frameworks that you use to target these devices are still somewhat up in the air. Like actual support for NPUs through DirectML is still not very mature. The LiDAR-T story around NPUs is still not very mature. And so we are building out the infrastructure that we need to answer these questions, but we have enough of it that we have some answers, but not, especially the GPU in the NPU space. We don't know yet. I'm hoping to have a better idea by like the middle to end of this year.
One of the things that maybe isn't quite called out, but with so many WebNN folks, maybe we can also like answer that question, is kind of the thing that's concerned me over time is this tight OEM integration type of a thing where you don't have these dependencies on OS primitives, which is, I mean, we do that to some extent on hardware primitives, but not necessarily on OS primitives. That's a much tighter integration over time. So when one of these, when OSs decide to change something, then that has direct implications on end applications unless you have a good migration story for it. And I think that's just challenging in general, where with different primitives, maybe you can work around it. In general, I'm a fan of having high-level APIs. It's just maybe how do people feel about the strong ties to OSC primitives or OEM dependence?
I think it's the job of the operating system to provide an abstraction over the hardware. I think what we're seeing in the challenges here is that the hardware is still too new for there to be a really stable OS abstraction. And I think that what we see in the graphics space, right, is that people don't write, and like the Dawn doesn't have NVIDIA code and AMD code, at least I hope. Mostly just direct 3D and Vulkan and Metal. And it's unfortunate there are 3 different frameworks there that we have to play. Like I feel like actually the comparison between like what we do in Dawn and what we do in WebNN is very similar. That each of the sort of 3 major platforms has their own OS abstraction for doing this, and we have to map whatever primitives we're exposing to the web to that platform level abstraction. But those are things which in that case, are much more mature frameworks than what we're dealing with in the ML space, because ML is just still very, very new and rapidly shifting.
Yeah. We also have flexibility in how we'd approach this. So Chrome will always be shipping, not always, but for the foreseeable future, shipping light RT with at least a CPU delegate in there. So you could imagine that if some platform that we wanted to target either didn't have one of these underlying frameworks, or they just discontinued it, or it was insufficient for our needs, or it had just stalled, and we could realize with a GPU delegate we could get better performance, then yeah, we could just move to using the underlying framework being one that was entirely provided by Chrome, and other browsers would have the same option.
We would generally prefer to ship less code with Chrome, right? So like in the options, like on Windows, for example, right, we have like to target an Intel NPU on Windows. You can use like OpenVINO via DirectML, or you can use OpenVINO being Intel's library for GPU and NPU. Like that's kind of their driver layer. You can get to that library via the Windows sort of hardware abstraction, or you can just depend on it yourself via frameworks like LightRT, or just directly in Chrome if you really wanted to. But the disadvantage of those options is that now means you're responsible for shipping and maintaining that library. And so if the OS is providing a higher level abstraction that still provides you what you need, then we would rather use it.
Cool. 2 minutes to go. Anyone got a final question?
So the Google's first party service, which is Google Meet, moving from, I think your example before, it used to use WebGPU and now you moved it to WebNN. Is that fair to say for the video?
I believe Meet is actually all still Wasm, or have they done also WebGPU now?
So Meet is primarily WebGL for GPU acceleration today, and we've been working with them for years now on a WebGPU backend, which is still nascent because they've got a couple of fallback paths to the CPU, which when they're activated are slower on WebGPU than they were on WebGL. We're working on addressing that with JSPI and optimized implementations of the async APIs in Chrome. Anyway, we're trying to get more to like compute-based implementation of like background blur and some of the other effects, as opposed to doing it all in fragment shaders in WebGL, which is kind of a hack, but it's a miracle that it works and as well as it does.
I do have a prototype that moves some of Meet's compute over to WebNN, but that's like a proof of concept to make sure that it actually works.
Works on Emily's machine.
It works like it works like the point is like that is waiting behind like also like priority wise, given WebGPU exists, the WebNN is still experimental. We're much more interested in getting that migration completed before we consider other less mature options.
Yeah. Folks from the Meet team have spoken up at the Web Machine Learning Working Group, bringing use cases like consider that how we might solve this problem. So yeah, that's about as far as it's gone. Thank you.
Cool. All right. With that, we're at time. Thank you, everyone.